geometrical isomerism. So geometrical isomerism, it is type of stereoisomerism, and it arises due to difference in the position of ligands in the space. So here the prime condition for this geometrical is it is exhibited by the compounds in which the central metal atom has coordination number or the secondary valency 4 and 6. Coordination number or the secondary valency, coordination number or secondary valency of central metal atom is either 4 or 6. Now see this complex. Here the Cl is on the same side, and here this amine is on the same side. So it is said to be cis isomer. Whatever the name is, the word cis is written before the name. Cis means on the same side. So this will be said to be the cis isomer. Again I am repeating, isomerism is said to be geometrical in which there is just exchange in the position of ligands, and it is exhibited by only the metal, central metal or metal ion having secondary valency or the coordination number 4 and 6 only. So here it is 4, and here the 2Cl is on the same side, one side, 2 amine on the other side. So they are in the adjacent position, and so this isomer, this type of isomer is said to be cis isomer. So if you write, say it is diamine dichlorido, platinum second, diamine dichlorido, platinum, second ion. So because see this amine, it is neutral ligand, so it will be what we say here. We say here diamine dichlorido, platinum second, diamine dichlorido, platinum second, because amine it is neutral ligand, no charge. So if you calculate, so here it is -1, so it will be second. Now this isomer, it just needs the exchange in the position. Here one NH3 is present as it is, one Cl is present on this side. Now in this other case, there is the exchange in the position of ligand, and so here NH3 gone to this side, Cl come to this side. So here there is the change in the position. Adjacent position is not maintained, symmetry is not maintained, and so this isomer is said to be trans. Here we write cis, and here we write trans. Again same, trans, before the name we write trans diamine dichlorido, platinum second ion or whatever. So this is said to be the geometrical isomerism. Isomerism is very important property of coordination compounds also. So coordination compounds also exhibit optical isomerism just like the organic molecule. So optical isomerism may be defined as the property of some enantiomers. See, in case of optical isomerism, the isomers are called as enantiomers. Enantiomers. We generally don't call optical isomers, but we call enantiomers. So enantiomers, they differ from each other in one point. that one enantiomer is called as deformed or dextrorotatory. It is called as dextrorotatory. Other is called as levorotatory. Dextrorotatory enantiomers are those which rotates toward the right side. Dextro rotates the plane of polarized light. Dextrorotatory enantiomers, they rotate the plane of polarized light toward the right side. Right side rotation. Levo rotate toward the left side. So what is the meaning of left and right side? Actually, we study optical isomers with reference to the ability of an enantiomer to rotate the plane of polarized light. You know, so see, ordinary light has the photons. So in case of ordinary light, the photons, they rotate in all the angle, that is 360. The photons or quantas, they rotate in all the directions. When this ordinary light is passed through Nicol prism, this is Nicol prism, then Nicol prism is used. In place of Nicol prism, we may use a spectrometer. A spectrometer can be used. A spectrometer, or we may use monochromatic light. Monochromatic light in place of this Nicol prism. So Nicol spectrometer can be used, or monochromatic light can be used. Either Nicol prism or spectrometer, or monochromatic light. So on passing ordinary light through Nicol prism, we get the quantas, we get the photons in one direction. So this is monochromatic light, that is light having one color, one wavelength. So this is also, so either we take, but this is a historical point of view. So this we study, we take the monochromatic light. So monochromatic light on passing through the enantiomer. So this we have here in the second part. This is monochromatic light, and we take here vessel in which enantiomer is present. So this enantiomer has the capacity to rotate the axis either to the left side or to the right side. Only one will happen, either to this left side. This is left hand rotation. This is left hand rotation. So here enantiomer will be levo rotatory. Enantiomer or optical isomer which rotates the plane of polarized light toward the left side. This is left side turn. On the other side, if you do the same, here we have the enantiomer, and here there will be the right hand rotation. This is the right hand rotation, and in this condition, here the enantiomer will be dextro rotatory. So this is the basic idea about the optical isomers. So optical isomers, they are called as enantiomers. Now other part is that optical isomers, they are sensitive to the plane polarized light. As they are rotating the axis of the plane polarized light, it means they are capable of changing the direction of the rotation, or the direction of the quanta is rotated either to the left side or to the right side. So such enantiomers are called chiral objects. Chiral objects means they cannot be superimposed on their mirror image. Object is said to be chiral when they cannot be superimposed on their mirror image. No superimposition. See, I have this one palm and see this is other. So they are similar. Here I am keeping. So this is superimposition. They are mirror image. So this is superimposition. So this is said to be a chiral. A chiral means when the object cannot be superimposed on its mirror image. So this is said to be chiral. So chiral objects, they cannot be. So this is a chiral. Other example of chiral objects. Let take the letter K. Now here there is the mirror. This is mirror. This is object. The image will be like this. This is object. This is image. So this cannot be superimposed. So this is said to be chiral. What about a chiral? Like see, A. Letter A. This is object. This image here, they can be superimposed. So this is said to be a chiral. It means a chiral is a condition when the object can be superimposed on its mirror image. So this is the object and this is the image. So the object can be superimposed. So here this will not be optically active. So this will not be optically active. So coming to our main point, these were the basics of the optical isomerism. So optical isomerism, it is studied a lot in her classes in physics. So now coming to main point. So optical isomerism is the property due to which the enantiomers are able to rotate the plane of polarized light either toward the right side or toward the left side. And so we say that enantiomers are able to change the axis of the polarized light or plane polarized light. Now see here, I have drawn an enantiomer. See this enantiomer, and here it is unsymmetrical. Optical isomerism is exhibited by the substances which are not symmetrical, non-symmetrical molecules. So non-symmetrical molecules. So here this will be having the octahedral geometry. So octahedral, you have to keep in mind, octahedral geometry is exhibited. So this is cobalt as central metal atom. So here ethylene diamine, three ligands are attached. Ethylene diamine is bidentate. So here it is forming octahedral complex. So this is the object. This is the object. Here there is the mirror, and so its image will be formed just opposite. This is object. This is the mirror image. So this cannot be superimposed on this. So here superimposition means if we lift and keep it here, so they cannot be superimposed, or it cannot coincide. How? See, this En is toward the left hand side. This En is toward the left hand side. This toward the right hand side. Here this En is on the left side. Here this En is on the right side. So none of the three groups are going to coincide. So here this is the point that they cannot be superimposed, and this condition is said to be chiral. So chirality, this behavior is called as chirality, and chirality is the prime condition for optical isomerism. This is the first and this is the second. Both they complement each other. Both have to be present. If any molecule, any enantiomer is optically, it is unable to change the plane of polarized light, it means it is achiral, so it will never be optically active. So here automatically this will be, molecule will be obtained. So just it's very interesting to know that this first will be called as dextrorotatory. It means it will rotate the plane of polarized light toward this right side, and its mirror image will be another enantiomer isomer. This is very important point. Object will be one enantiomer, its mirror image will be the other. It will call the levorotatory. Levorotatory rotates toward the left side, dextrorotatory rotates toward the right side. So this is all about the isomerism.